In this question, we will primarily look at the death rate estimate computation, because if we just go through this question once. Two neighboring small countries have for many years taken their annual census of their populations on 1st January, in which each inhabitant must give his or her age. So the population is collected on 1st January. Country A uses age last birthday, whereas country B uses age nearest birthday. Right? Each country has also operated a system in which the deaths are recorded on the age nearest birthday at the date of death. Alright. On 30th June, a country A invaded country B and the two countries became one state. The new government wishes to estimate the single set of age specific death rates for the new unified state using the census data taken in the years before the invasion. So we have to find out the mu x. All we need to see for mu x, the computation of the mu x, we are very much clear. It is the number of deaths during the particular period for a person whose age is x, and I divide it by the central exposed to risk. The central exposed to risk during that particular period. So now my intention is to go ahead with first computing the central exposed to risk, and now that we have the deaths and most of the cases in both the countries, the deaths are recorded on age nearest birthday itself. So we just need to make based on the principle of correspondence, I need to make the exposed to risk also. I need to compute the exposed to risk in such a way that if a death is, if a person had died whose age is X and he has been included in the death, then that number should be included as a part of the exposed to risk as well. So a major exercise is in terms of adjusting the exposed to risk data, because in both the countries we are seeing, as far as the deaths are concerned, we are seeing that they have recorded it on age nearest birthday basis, whereas in case of the census, the age, we are looking at one country defining it on last birthday, whereas the other country has still defined it on the nearest birthday basis itself. So when I am going with the typical deaths, right, I could represent it with theta xt in case of country A, and I can take it the same theta xt for country B. A person aged X, the person's aged X in country A and B, the number of deaths that are being recorded is directly coming up with this kind of a mechanism. So at least when we are going ahead with, and these are both on a nearest birthday kind of a basis. So mu x needs the actual force of mortality is just mu x. The rate is more of a mu x, which is applicable to the exact age x, and it does not require any kind of a modification. But look at the population. We look at the population on 1st Jan. When I am seeing that 1st Jan population, probably if at all it is some pxt for A and pxt for B. Let's say these are the populations as per the collection mechanism. Right? Now, when I am looking at the central exposed to risk, when I am looking at the central exposed to risk, I'm simply looking at I'm simply looking at in case of A and B, I'm looking at that particular mechanism, the central exposed to risk for A. I can look at it as the average, because on 30th June is what I am looking at. So the average of the population, I'll take it as P star, the average of people whose age is X, and the average of the people whose age is X in T plus 1. The same logic will work out for B also. If I have to find out the central exposed to risk in case of B, all I am looking at is some kind of P star, where we are talking of it's an average of the population whose age is X at time T, and the population whose age is X at time T plus 1. This is what will go as the central exposed to risk, because we are simply assuming that the population varies linearly between the census dates. So, whereas when I look at this particular population of A, it is actually collected on the age last birthday basis. Right? It is collected on age last birthday basis, which means I could very well define the P star X comma T for A. I can define it as the average of, because I am looking at the age last birthday. If I want to convert it into age nearest birthday, I can look at the average of the people whose age is X at time T, and whose age is X minus 1 at time T. Because if I have to take it into the age nearest birthday basis, but I have collected the data on age last birthday, some of them will be having age X and some of them will be having age X minus 1. Whereas in case of at least B, that problem does not exist, because they have collected the census on age nearest birthday basis itself. So we can see in case of B, the P star and P, both of them are the same. Now, with this kind of an information, I can very well go further in terms of computing, in terms of taking up the overall exposed to risk for A as well as B. Now, central exposed to risk for A comes out to me as first the weighted average of, I'm looking at X and X minus 1. So, half the population whose age is X at time T, population whose age is X minus 1 at time T, and at the same time I am again taking the population whose age is X at time T plus 1, and the population whose age is X minus 1 at time T plus 1. So this is what is working out as central exposed to risk for A, whereas in case of B it is straightforward. I am taking the population whose age is X at time T plus population whose age is X at time T plus 1. So this is what is contributing to the central exposed to risk for both A and B. And now that we know the total number of deaths, which we have initially assumed that theta X plus T, X at time T for A, and theta for age X at time T for B. So this number divided by this number is going to give me an estimate of mu X. The only difference that is coming up here is, probably in case of B, the population recording as well as the deaths recording both are happening as a part of the age nearest birthday basis itself. Whereas when it comes to A, the deaths are recorded on age nearest birthday, whereas the population census is recorded on age last birthday. So when a person's age is 30, let's say last birthday, but if I have to convert it into the nearest birthday basis, then probably we are looking at he could be either 30 on a nearest birthday basis, or he could be 29 on a nearest birthday basis. So that is the reason at time t we are taking the ages x as well as x plus 1 to convert the age last birthday. If his age last birthday is 30, then probably from a nearest birthday basis I need to take it as the same age last birthday for the last year, and that is where we are using this kind of relationships to first compute the updated central exposed to risk, and for deaths we are not making any kind of a modification. So both taken together are used in computing the estimating the mortality rate for our numerical. All right. Now let's look at this particular question where we are trying to estimate the rate estimation based on the experience. These are some kind of typical questions that we need to understand. So probably just if we go through the question, an oil company has discovered a vast deposit of oil in an equatorial swamp. That area is unhealthy, where there are venomous spiders, and there is an antidote available, so nothing too much to be panic, but is expensive, but does not, it only acts instantly but not future immunity. So there is a study that is being performed. So the company has posted its employees for 6 months tour. So starting 1st Jan, 1st April, 1st July, 1st October. So at the beginning of each of the quarters, the employees are being posted to that particular location. All right. So let's use a spreadsheet to work it out. So if I'm saying that I'll keep an estimate, or let me call it as a, a rate estimate, right? Let me call it as a rate estimate. Here, what are we saying? The quarter beginning, okay, quarter beginning, and we are talking of number of new arrivals. All right. So how many people have come at the beginning of each of the quarters? So we are talking of 1st Jan, number of arrivals being 90 new arrivals. Similarly, 1st April, we are talking of 80 new arrivals. 1st July, we have 114 new arrivals, and 1st October we have 126 new arrivals. Fair enough. Now what are we saying? So people have posted in that way. The first employees to be posted arrived on 1st Jan. Swamp is so inaccessible that no employees are allowed to leave before the 6-month tour. Fair enough. Accidental deaths are common. So here we are talking of two types of problems. One being an accidental death, two being the spider bites. Alright. So if I am talking about accidental deaths, we are saying that during that particular period, there are 10 deaths here, 8 deaths here, then 10 and then 13 deaths during this period, and number of spider bites, right? The spider bites might have got cured because there is an antidote for it. So we are talking about number of spider bites as 15, 25, 30 and 40. Now my intention is estimate the quarterly rate of being bitten by a spider. The quarterly rate of being bitten by a spider in each of the quarters. That is what is our intention. Now what I need to know for that is, okay, I know during this period these are the bytes. Now for me, I need to understand first of all what is the total exposed to risk during each of these quarters, right? How many, what is the total number of people on an average is the exposed to risk. So what I'll do is here I'll find out the central exposed to risk in each of these quarters. The first thing that I would like to do, because in the first quarter there is nothing much. We are seeing that the people have come, 90 of them have come, out of them 10 of them have died. So the number who have survived, probably before getting into central exposed to risk, I can talk about survived during the period, right? Number of people who have survived during the period. In this case, I can very well say 80 of them have survived during the period, right? 80 of them, but that need not be the case here. We'll come back why we are saying that need not be the case. But during this period, number of them who have survived is 80. So, central exposed to risk this time is like, here the risk I am looking at is in terms of the spider bites, people who are available and who could be accessible to a spider bite during this quarter. Because there are 10 deaths, I am assuming that these 10 deaths would have uniformly died. I am making an assumption here. The deaths that have happened, accidental deaths that have happened, I am making an assumption that they are uniformly distributed across the quarters. That's one assumption that I am making. If that's the case, their contribution to the central exposed to risk is always 50%. Right, because I am assuming that they have all died uniformly over the period, so on an average their contribution is 50% to the central exposed to risk. So at least for the first quarter, I can say that the central exposed to risk is all 80 people, they have got a full exposure, whereas the 10 people who have died during the period, they have got a 50% exposure, making the overall central exposed to risk of 85. Right? Now, by the second quarter, I have these 80 people who have survived and the 80 people who have come new. So I have overall 160 people. So what has happened is, out of them 8 of them have died. So basically in the second quarter, at the end of the second quarter, the number of people who are survived is 152. So if I have to go with the central exposed to risk here, 152 people, it's a one central exposed to risk, whereas for 8 of them it is 0.5, making the overall central exposed to risk is 154. Now, this is where the catch comes up. In the third quarter, the people who are left in the first quarter, they are the people who have arrived in the first quarter, they must have left. So, what is the number of people who are there in the first quarter? 80 of them were there in the first quarter. 80 of them were there in the first quarter. 80 of them joined in the second quarter. And out of them, 8 of them have died. So, I can very well assume here that 4 of them from the first quarter and 4 of them from the second quarter might have died. So making this the survived. So the total survived, if I have to look at it, I will look at this 156, 152, whosoever have survived. Out of them, I will assume that 76 people have left and they are joined by 114 people who are new, and which is resulting in out of that particular total, I am saying 10 of them have died. So making the number of survived during this period is 180, which is helping me to come out with the central exposed to risk saying 180 times 1 plus 10 times zero point 0.5. I hope this calculation is clear. Right, we are saying people have left. People who came in the first quarter, they have left in the second quarter, and we have made the assumption that these are the number of people who have, because 80 of them were there in the first quarter, 80 of them in the second quarter. So the people who have out of the 8 who have died, because of the proportion, we can assume that 4 of them of the first quarter died, 4 of them of the second quarter died. So the remaining 76 who were alive, they were sent back. So based on this, I have got that the total number of people who are remaining is this much. Out of them, 10 of them have died, which has resulted in the exposed to risk being equal to 185. The same way I can operate out for the last quarter, right? Let's say at the end of the second quarter, third quarter, 180 people have survived. 180 people have survived. They are joined with 126 new people, and this is where I really need to see the existing set of people. Earlier there were 76 people and they were joined by 114 and there were 10 deaths. So out of which I could assume that 76 out of 190, 76 out of 190 could be the number of people. Now here this is where out of this 80, 4 of them have died in the second quarter itself, which means only 76 of them are alive. And out of this 10 who have died, if I look at it proportionately, it is nothing but 76 divided by 76 plus 114 new people. So around 40% of the people have died, which means out of this 10, I can very well take 4 of them from the previous period, 4 of them from the second quarter dying off. So 8 out of 80, 4 have died in the first quarter, 4 in the second quarter, making 72 of them alive who can go back. So from that I can say that the number of survived during this period is 180 plus 126 minus 72 minus 13. So the number of survived during this period is 221, and taking it to the central exposed to risk, I am getting it as 221 times 1 plus 13 times 0.5. So working it out to 227.5 being my central exposed to risk during this part. So from here I can very well take the rate of being bitten. Now I have the central exposed to risk and exact number of spider bites. So I can look at the rate of being bitten as the actual number of bites divided by the central exposed to risk, giving me that around 17%, 17, 16, 16 and 17. So these are the typical numbers that I can compute for the estimate for the rate. And here I am making an assumption that because of the antidote that is available, all the people who are exposed to risk, who are being bitten, they are all fully cured. But the major thing we have to understand here is, in this case, we are only looking at accidental deaths as the other form. We did not look at natural deaths or any other form of death. That's one assumption that we might have gone with, and that's something which might be a bias as a part of our calculation. In general also, probably when a person or when a team is visiting a dangerous place, we see that the accidents are more possible in the initial periods, but they may slowly come down in the later periods because of the experience that the team gains, and probably the kind of initial steps they take care to protect themselves. So because of that, there is a possibility that the deaths are more higher during the initial quarters, or probably in the beginning periods of the quarters for the new team, because when a new team comes, there is a possibility that they don't get adjusted to the circumstances, and there is a possibility that they get more and more exposed to the bite. But keeping all these things aside, if I am looking at a uniform distribution of the accidental deaths, and I am assuming that the spider bites are more or less uniform across the period, these are the typical numbers I can operate for the estimation of the rate of bite. More or less, you see, 17 and a half, 17.6, 16. So we are seeing a pattern like in the initial periods it was higher, in the middle periods the rates have slightly gone lesser, but again it got slightly higher. But overall we are seeing a uniformity in the pattern for each of the quarters as a part of the rate estimate, right? So this is how we can compute whether it is a mortality rate or any kind of hazard rate estimation. I need not call this as a mortality estimate. Any kind of a hazard rate estimation from the experience based data can very well be computed through this kind of a model. All right. Now let's look at a numerical that is concerned regarding the calculation of the mortality rate using the central exposed to risk as well as initial exposed to risk mechanisms. We know that the central exposed to risk, if at all I have to clearly understand what is the central exposed to risk, in a simple statement I could very well talk about it as the waiting time. The waiting time for the overall observations, the total waiting time of the observations when we bring out either a multi-state model or even a special case, a two-state model, or probably even a Poisson model. It's an overall waiting time which we generally denote it as the with a C at the top. The exposed to risk with a C at the top is giving me the central exposed to risk. Especially, we will try to calculate the central exposed to risk by collecting the waiting time, by collecting the time for which a particular party is included as a part of the observation. So if that party has died, we will remove that party from the observation immediately. So the contribution to the waiting time stops the moment the person dies when we are looking at computing the central exposed to risk. But when I talk about the initial exposed to risk, I take the entire rate interval. Just the entry of the person is important for me. I will consider the entire rate interval for computing the waiting period. So I'm considering the entire rate interval for computing the waiting period. That is the reason we generally put in a simpler way the central exposed to risk plus whatever is the difference in time between the end of the rate interval minus the date of death for all the participants who have died during the period, who are observed to die during this particular period. When I look at the central exposed to risk and I add up the difference between the end of the interval and the date of death, we are arriving at initial exposed to risk. So in general, we see an approximation kind of a calculation also. Whenever I have to find out the initial exposed to risk, I look at their central exposed to risk, and assuming that the deaths happen uniformly across the period, we will compute it as 0.5 times the number of deaths that have occurred during the period. This is a kind of an approximation relationship, though not exact, approximation relationship between the initial exposed to risk and the final exposed to risk, right? So that's a clear cut differentiation we bring in terms of calculations. So whenever we are looking at the central exposed to risk, I only observe until the time of death. But when I am looking at initial exposed to risk, my observation is initially exposed to risk. So I am not bothered about their deaths intermediately. I am more bothered about initially what is the amount of time, these particular parties are going to spend as a part of the observation process. All right. So we'll use this numerical to try to understand the differences very clearly. But just as a quick note, the central exposed to risk, whenever we are considering, we generally use this central exposed to risk to generally estimate mu x, which is the force of mortality. But whenever I am working with initial exposed to risk, I generally use it to estimate the discrete probability of death, which is the qx form. So even if I am using the central, probably finding out mu x, we have a formula to convert that mu x into qx. We have seen earlier the qx from mu x comes out as 1 minus e power minus mu x. So I can use this kind of a logic to typically compute the qx from mu x. So those kind of interlinkages can very well be applied to really solve our numericals. Alright. So let's look at a simple numerical which will address all these things. An investigation studied the mortality of infants aged under 1 year. Okay, so they are all like zero aged kind of people. So I am more interested in finding out Q zeros and mu zeros. Following table gives details of 10 lives involved in the investigation. Infants with no date of death were still alive on their first birthday. So out of the 10 lives which we have observed, 3 of them have died during these time periods, right? So so from the date of birth, I'm doing some kind of an observation for them. So here it is like when I have to look at their contribution to the central exposed to risk. Now the first thing I would like to do is the central exposed to risk. Central exposed to risk, if I have to find out, I'll look at the contribution of each of these persons. He was born on 1st August 2008 and not yet dead. So which means the contribution is 12 months. Similar, 12 months. But this person born on 1st December 2008, dead on 1st February 2009. So the contribution is just 2 months to this central exposed to risk. For the 4th life, still alive. So 12 months. 5th life, 12 months. 6th, born on 1st March, dead on 1st December. So there is a contribution of only 10 months to the central exposed to risk. 7th life a full 12 months, 8th life a full 12, 9th a full 12, and whereas the 10th was alive only for 1 month. So overall, if I am looking at the central exposed to risk, okay, this party 1st March, 1st December, only 9 months, not 10 months. So overall the contribution is just 96 months. 96 months translate to 8 years. So if I am looking at central exposed to risk calculation, we say it is 8 years. But if I am going with the initial exposed to risk, if I am using the approximation formula, I'll use it as central exposed to risk plus half the number of deaths. So the initial exposed to risk will come out to 9.5 under the assumption that the deaths are uniformly distributed over the period. But if I am going from an actual calculation perspective, my initial exposed to risk is 10. So either of the mechanisms I can go with. Either I can approximate it using this kind of a formula, or I can take the actual value, which is the total number of observations at the beginning of the period. Now, the question comes, calculate the maximum likelihood estimate of the force of mortality. We know that the maximum likelihood estimate of the force of mortality, if at all I am going with a two-state model, is nothing but the number of deaths divided by the central exposed to risk. So we have seen that there are 3 deaths and central exposed to risk is 8 years. So overall working out to 0.375 being the central being the maximum likelihood estimate of force of mortality. So here I can look at maximum likelihood estimate is coming out to me as 3 deaths out of 8 years. So 0.375 works out to mu naught, which is the maximum likelihood approach estimate to the force of mortality. But we are more interested in finding out the infant mortality rate Q0. So for me, Q0 comes out as 1 minus e to the power of minus mu 0. So I'll write it as 1 minus e to the power of minus mu 0, which works out to around 0.31. So using this kind of a mechanism, if I have to find out the Q0, I'm getting it as around 0.31. But when I'm going with initial exposed to risk, I can directly use Q0. I will directly get Q0 only, number of deaths divided by initial exposed to risk. So either I can take, if I have used initial exposed to risk as an approximation from central exposed to risk, I'll take it as 9.5, get this number. Or if I'm using the initial exposed to risk as 10, I'll get this kind of a number. So there are two different calculations, but the first answer that I am getting 0.3157, it is under the assumption that the deaths are uniformly distributed over the age between 0 and 1. Whereas whatever we have computed using this mechanism, it is assuming that the force of mortality is constant. This is going with uniform distribution of deaths assumption, uniform distribution of deaths during the mortality period, during the observation period, whereas this is talking about constant force of mortality between the ages 0 and 1. And when I am using this mechanism, I am not making any assumption regarding the initial exposed to risk, even about the shape of the force of mortality. No assumption, I am just carrying that the overall number of observations at the beginning of the period is 10. So different kinds of assumptions are leading to different estimates regarding the mortality rate Q naught. So we need to be very much comfortable regarding the estimates and the assumptions that is going into the computation of each of these estimates. Alright.